Hey folks, today I figured we would do a video because I've had some requests on solving equations using the property of logs. I went ahead and printed out my notes that I would have given you in the classroom, and we're going to work some examples so that you have a lot more examples worked out for you and you can see exactly how to do them. So I think all in all there are, let's see, like 11 examples. We may not do all 11 in this video, but I'm going to do as many as I can. That way you can see a lot of them, and feel free to pause, rewind, rewatch, fast forward, whatever it is that you feel like you need to do. I figured we'd start out with the properties of logs, and I've got it on a little index card so that I can take it in and out of the frame whenever I need to. So the first thing that we want to write down is the product property for logarithms. So for the product property, if I have log base b of m times n, then I could rewrite that as log base b of m plus log base b of n. So that's the product property. The quotient property is similar, but instead of using multiplication and addition, you use division and subtraction. Those two go together. So if I have log base b of some quotient, so some division problem, maybe m divided by n, then I can rewrite that as log base b of m minus log base b of n. And then the last one that we have is the power property, which is really cool. So if we have log base b of some argument m to the power of k, then we can rewrite this, taking this exponent and bringing it out in the front. We can rewrite this as k is the coefficient times log base b of m. So this is our properties of logarithms card that we're going to move in and out of the frame whenever we need it. So I'm going to go ahead and take it out of the frame for now. I'm going to slide my notes in. So if we're solving logarithmic equations, the Logarithm Law of Equality says that if b, x, and y are positive numbers, which we know x and y will be positive numbers, and b should be as well, and b is not equal to 1, then log base b of x equals log base b of y. That is true if and only if x equals y. And what if and only if means? I guess I should have circled the if too. Means if you have this, then you can say x and y are equal. And also, if you have an x and y that are equal, you can build this equation out of it. You can take the log base b of both sides. So it kind of goes both ways. If you have one, then you have the other. If you have one, then you have the other. So the way that you're going to solve logarithmic equations, and we'll come back to this because we're going to use it for this example. So the way that you solve logarithmic equations is if even one of your terms is a non-log term, then you're going to move all the logs to one side and all the non-logs to the other side, condense the logs using your properties of logs, and then change to exponential form. So we see that as example 1. Example 1 has this term and this term that are non-log terms. So we're going to move both of these to the other side, and then we're going to condense the logs, and we're going to go ahead and solve. So I'm going to move this to the other side with subtraction. I have 2 log base 2 of x equals 25 minus 15, which is 10. Okay. And I'm also going to, I've got a couple options here. But what I'd like to do is I'd like to take this, and either I can put it up here as the exponent, or I can divide both sides by 2 because it's still 2 times this logarithm. So I'm going to go ahead and do that. I'm going to divide by 2. And I have log base 2 of x equals 10 divided by 2, which is 5. So now I'm going to change to exponential form. I'm going to exponentiate this. So the base was 2, so I'm going to make the base 2 on both sides. 2 to the power of log base 2 of x means that these cancel out, and I'm left with just x equals. And 2 to the power of 5, you can check in the calculator, is 32. There we go. So this is a problem where you have at least one non-log term. This is what you would do. And we see that again on number 2. So we have at least one non-log term. Which is it? It's this minus 2 right here. So I'm going to get all the log terms on one side and all the other terms on the other side. Let me see if I can zoom this in a little. Maybe a little bit better. Yeah, I think that's better. Okay. All right. So I'm going to try and move this over here and this over here. So the best thing to do is to get rid of this guy first. So plus 2, there we go. Log base 8 of 4 equals negative log base 8 of x plus 2. Now I want this log over here on this side, so I'm going to add log base 8 of x, add log base 8 of x. Those are gone. And I have log base 8 of 4 plus log base 8 of x equals 2. So I'm going to bring my properties of log card in here. And I notice that I have addition between two logs with the same base. So that sure looks a whole lot like the product property. Two logs, same base, adding them together. That means that I can make them one log with that base and the product of those two arguments. So this is log base 8 of 4 times x equals 2. So I'm going to have to continue this out here, and I'm just going to rewrite because I need my problem. Okay, I'm going to change to exponential form, so I'm going to exponentiate. I'm going to make the base 8 on both sides. That will cancel out the log, so I'll have 4x equals 8 to the power of 2, and 8 squared is 64. And now I have a nice simple equation to solve. If I divide by 4 on both sides, I get x equals 16. Sorry. Been out of practice for a long time. There we go. Okay, so we have another problem that's like that here. I think I'm going to go ahead and turn the camera off and solve it and then show you the work. I'd encourage you to do the same thing. Turn your video off, pause it, and then turn it back on and see if you can get the right answer. Okay, so you can go ahead and check your work with number 3. I did notice that there were 2's in all of the terms, so I did kind of divide by what I thought was the greatest common factor. I know that we're not factoring here, but I did divide by something that I knew I could take out of all 3 terms, and that made everything a little bit simpler. I could have just as easily taken by the power property this 2 and made it the exponent, and this 2 and made it the exponent, and that would have been just fine as well. So I'm going to go ahead and open this up to number 4. Okay, let's see. I feel like even closer would be good. There we go. It's tough with the shadow that's in the way. Okay. All right, so for number 4, I noticed that there are no non-log terms. So now I've gotten to the point where I'm at the second bullet, and the second bullet says, if you have all log terms, condense to a single log on each side and then use the law of equality. So if you condense to a single log on each side, then you can use the law of equality to just say that this argument and this argument are equal. You can say x equals y. So you want to get one log term on each side. So let's use our properties of logarithms. I'll go ahead and put that right here, just because I know we're going to use it. So I only have one log on this side, so that's good. Log base 2 of x equals. But I do have two logs on the right side, and one of them has a coefficient out here. So by the power property, I can take that coefficient and I can actually make it the exponent of that argument. So I'm going to take this, I'm going to make it the exponent. So this is log base 2 of 3 squared plus log base 2 of 5. And we know 3 squared is 9, so we're going to keep that in mind in just a second. The other thing that I see is I see the sum of two logs that have the same base. So that looks an awful lot like the product property. So I'm going to go ahead and multiply those two arguments together. So I have log base 2 of x equals log base 2 of, remember this was 9 and this is 5, and 9 times 5 together is 45. So I have one log term on each side. They have the same base, and so by that logarithm law of equality, if I have that situation going on, I can say that the argument equals this argument, right? So I'm going to go write that my x equals 45. If I take log base 2 of something, it better equal log base 2 of this over here. So that something must equal 45. Okay. So for the next, actually, maybe I'll do another one. I'll do another one kind of talking through it, and then some of the other ones I'll work a little bit faster. So on number 5, here's my equal sign, in case you couldn't see it. So I have 3 log terms on this side. They all have base 7, and 1 log term on this side that also has base 7. So I'm going to start using my properties of logarithms. I'm going to add these two, which means that their arguments need to be multiplied. So I'm going to have log base 7 of x times x, that's x squared, and then these are both log base 7, but I'm subtracting, so that means I need to use the quotient property. This is going to be log base 7 of x squared divided by 3 equals log base 7 of 12. By that logarithm law of equality, I can say that x equals y here. So again, by that logarithm law of equality, I can say that x squared divided by 3 equals 12. And now we have a situation where I can just solve for x. So I can multiply by 3 on both sides. I can get x squared equals 12 times 3, which is 36. Aha, to undo a square, I square root. And the square root of 36 is plus or minus 6. However, we know that if I take a negative 6 and I put it in here for x, 7 to no power will give me a negative 6. So that means that negative 6 is extraneous, and my solution is just 6. Negative 6 is extraneous. Okay. So I'm going to work the next few, but I'm not going to work them and give so much elaboration. It's going to be a little bit more quiet, so as you feel like you need to, go ahead and pause, rewind, rewatch, or skip around. So this is the quotient property. Log base 8 of 48 over x. Log base 8 of 4. The logarithm law of equality. So we have 48 over x equals 4. 48 equals 4x. X equals 48 divided by 4, which is 12. Okay, here's my equal sign right here. I'm going to move this up here. We have log base 3 of x squared minus log base 3 of 4 equals, log base 3, this is addition, so this is product property. 2 times 8 is 16. Same base, but subtraction, so this is quotient property. log base 3 of x squared divided by 4 equals log base 3 of 16. The Logarithm Law of Equality says that I can set x and y equal to each other if I'm taking the log of both of them. So x squared divided by 4 equals 16. I want to solve for x by getting x out of that fraction. X squared equals 64. You can go ahead and check that in the calculator if you need to. And then to undo a square, you must square root, finding the positive and the negative values of that square root. But remember the negative value if I go substitute it right here. Actually, now that I think about it, yeah, I can't have 3 to the power of anything give me a negative 8. So my answer is 8. Negative 8 is extraneous. I'll flip it over. We have 4 more examples. I will walk you through number 8 though. Number 8 looks a little crazy, but it's not quite so bad. But nevertheless, I think we should walk through it together with commentary. So I noticed that all terms are log terms, so I'm going to try and condense to one log term on each side. I notice that everything has a base of 2, which is good. I also notice that we have subtraction, so that means this is quotient property. Log base 2 of 2x minus 1 over x plus 5 equals. I also notice that I've got some coefficients out here, so they need to become exponents. So we have log base 2 of, what is 36 to the power of 1/2? That's really the square root of 36, right? So that should be plus or minus 6. But again, I can't have a negative here as an argument, so that's going to be a positive 6. Minus log base 2 of 2 to the power of 2, which is 4. 2 squared is 4. So again, now that I've used my power property, I'm going to use my quotient property because I see subtraction between two like-based logarithms. So I have log base 2 of 2x minus 1 over x plus 5, and it equals log base 2 of 6 divided by 4. And by the logarithm law of equality, I can now say that 2x minus 1 over x plus 5 is equal to 6 over 4. I have a couple ways to solve this one. So what I would like to do is I would like to get this out of the denominator. So I'm going to go ahead and multiply both sides by the denominator, x plus 5. I also want this out of the denominator, so I'm going to multiply both sides by 4. Multiply by 4. So now this and this are gone. This and this are gone. And I now have 4 times this equals 6 times x plus 5. What should I do whenever I have a coefficient in front of kind of a binomial and I'm multiplying? I should distribute. So 4 times 2x is 8x. 4 times negative 1 is negative 4. 6 times x is 6x. 6 times 5 is 30. And now I want to get my x's on one side, so I'm going to move the smaller one. Minus 6x. 8x minus 6x is 2x. And I want to move the constant over to where this constant is, so plus 4. 2x equals 30 plus 4, which is 34. And if I divide by 2, I get 17. So my x value is 17. And I have not been taking these and substituting them in just because I know that they do work, and I didn't want to put that in the video because I thought it would take an extra long bit of time. However, I do encourage you to go back through and substitute those answers back in to show that you do in fact have the correct solution. So I'm going to go ahead and work 9, 10, and 11 a little bit more quietly with a little less detail. So these got log base 2 and log base 2, so by the law of equality, x minus 4 equals 2x plus 1. Well, that was easy. Negative 4 equals x plus 1, and x equals negative 5. Does that work out? Is that okay? Well, negative 5 minus 4 is negative 9, and 2 times negative 5 is negative 10, plus 1 is also negative 9. So I suppose that that would be the same. Log base 2 of negative 9 equals log base 2 of negative 9. But since I do have log base 2 of negative 9, because negative 5 minus 4 is negative 9, equals log base 2 of this would also be negative 9. And I can't take 2 and raise it to any power to give me negative 9. Truthfully, even though these are equal, they don't mean anything, because I can't take 2 to the power of anything and get negative 9. So this really doesn't give me an answer at all. So we say that this is no solution. Because whenever you substitute this back into your equation, you end up with negative arguments, and you can't have that. So this would have been something that we would have said was extraneous, but since it was our only answer, when we substituted it in and it gave us negatives, we say that it's no solution. I'm going to go ahead and do 2 more. So I already have my logs on one side and this isolated, but I do see a power property. So log base, it's log base 10 of 5 to the power of 2, which is 25. 5 squared is 25. Equals 2. Then we have quotient property. So the log of x over 25 equals 2. Remember that this is base 10, so in order to exponentiate it, we're going to go ahead and raise both sides with a base of 10. So we have x over 25 equals 10 to the power of 2, which is 100. I'm going to multiply both sides by 25. I have x equals 2,500. That's kind of a crazy answer, so I am going to go ahead and check that one. Check. I'll check it in pink. So log base 10 of x, which we found was 2,500, minus 2 log base 10 of 5 equals 2. This is what we are supposed to have. So we have log base 10 of 2,500 minus log base 10 of 5 squared equals 2. Log of 2,500 minus log of 25 equals 2. Quotient property, log of 2,500 over 25 equals 2. And let's see, this is log base 10 of, this would be 100, equals 2. And do you agree, remember that's base 10, do you agree that 10 to the power of 2 equals 100? Yes, we do. So that means that my answer is truthfully 2,500. Big answer. Okay, last one. So I'm going to move this over and this over. So we have log base 4 of x plus log base 4 of 6 minus log base 4 of 8 equals -1. I just moved this over and moved this over. I've got product property here. Log base 4 of 6x minus log base 4 of 8 equals -1. And then I have quotient property. So log base 4 of 6x over 8 equals -1. And I'm going to exponentiate. So I have 6x over 8 equals 4 to the power of -1. Remember, anytime you have a negative exponent, it means that you take the base and the positive exponent to the other side of the fraction. So this is 1/4, because 4 to the power of -1 equals 1/4, technically to the power of +1. And then now I'm going to multiply by 8, multiply by 8. 6x equals 8 over 4, which is just 2. And if 6x equals 2 and I divide by 6, I get x equals 2/6, which is really 1/3. So I would go back and I would double check that. All right, I hope this video was helpful. If you have questions, join my Zoom sessions or send me an email or a remind text. Have a good week.